Hello everyone. Today, we're going to continue working with the flexible cantilever beam. In the previous video, we simulated the beam under base excitation. But this time, let's take it a step further. What if we attach a pendulum to the tip of the beam? This setup actually resembles a tower with a pendulum-type tuned mass damper, like those used in skyscrapers to reduce sway. Let's see its effect on the beam's vibration. I'll start by using the model we built in the previous video. Since that model was set up for a hanging beam, I'll first rotate the coordinate. Rotate it -y so the base sits at the bottom. Okay, let's check the load case. It's already using motion input. Let me clean up the model. We only need the tip displacement, so I'll delete the rest. Then I'll add a new flexible beam. Let me just tidy up the layout. Now, I'll add a revolute joint to model the pendulum and connect it to the beam tip. Next, we need the pendulum mass. Let's adjust the beam parameters. I'll use a 50 by 50 millimeter cross section and 2 meters in length. I'll keep the default material properties. For the pendulum mass block, I think 0.1 meters looks good. And I'll define it as a point mass. Now we need a rigid transform to define the pendulum length. Set the translation to cylindrical, then input the radius. It creates the distance from the revolute joint, which gives us the pendulum length. Let's see the results. As you can see, the pendulum stays at 90 degrees from equilibrium. That's because the revolute joint rotates only about its z-axis, and this setup makes that axis lie along the beam's length, like this. So I'll rotate it by 90 degrees around the x-axis. To set the initial angle, I'll rotate it back by 90 degrees at this transform block. Let's see the result again. Perfect. I think that cube looks kind of boring. Let's switch it to a sphere. Define it as a point mass, and also change the color to make it easier to see. Now, for the torsional spring, this spring constant directly impacts the absorber's performance. We want the pendulum's natural frequency to match the primary system's resonance. The natural frequencies of a cantilever beam are given by this equation. So the first mode is about 64.59 radians per second. The pendulum's natural frequency is given by this equation. Let's say the mass is 1.35 kilograms. Based on my calculation, the required spring constant is about 350 newtons meters per radian. Here we go. I think it'll be better if we first compare it to the model without the pendulum. That way, we can clearly see the performance of the damper. This one here is the system with the tuned mass damper. And this one is without it. Alright, I'll connect it here. Then translate it in the x direction so the two models don't overlap. Before sensing, I'll translate it back to adjust the sensor's equilibrium. Let me just organize the model. Okay, To make them easier to interpret, I'll change their colors. Now, use a multiplexer to compare their responses. Okay, let's go with 3mm input at 64.5 radians per second. Alright, let's see the comparison. As you can see from this graphical plot, the beam with the pendulum damper has much less deflection. Let's take a look at the time responses. I think I did something wrong. Got it. I forgot to change the transform block direction. Here we go again. And there it is. The tuned mass damper works just like in the animation, greatly reducing the beam's sway. Let's zoom in so you can clearly see the difference. Okay. Now, what if we want to adjust the stiffness? We have two options, change the mass or the pendulum length. And I'm going to go with the pendulum length, which is adjusted to 0.19 meters. Let's see the results. You'll see that the result is still just as effective. Okay, as you know, a tuned mass damper is designed to absorb energy at a specific frequency. So now, let's tune the damper for the second mode of the beam. I'll keep the same spring constant and mass. So the pendulum length would be 0.03 meters. Oh, I think I forgot to change the excitation frequency. Alright, let's see. As you can see, the pendulum is pretty short. However, it still works very well. Let's take a closer look at the responses to see the difference. Note that these tuning values might not be optimal. They're just for demonstration purposes. I hope you found this helpful. If you have any questions or want to see a specific topic, let me know in the comments. Thanks for watching, and I'll see you in the next video.